Okay, great. So I'm really excited to introduce our next speaker, Josh McDermott. Unfortunately, due to a flight delay, Josh can't be here today. So instead, he's speaking over Zoom at a very inconvenient time in the middle of the night. Josh is an associate professor at MIT in the Brain and Cognitive Science department. And he describes himself as someone who studies how people hear. And I think this describes him very well because this is an incredibly broad research program. It covers everything from biological auditory systems to music perception to the kind of computational audio and audiovisual work that we've seen a lot of in this workshop. In addition to that, he started out in vision working with Ted Adelson. So I've personally learned a huge amount from Josh over the years. And so, as always, I'm very excited to hear what he has to say. Can we get him up on the screen? Sorry, we can't hear him. Can we get him up on the screen and hear what he's saying? Sorry, Joe.
Andrew, are we good to go, or should I start over?
You can start now. Yeah, sorry, there was an audio glitch there. We're good now.
Okay, all right, no worries. Great. Okay, like I was saying, thank you to the organizers for inviting me to do this. I'm sorry I couldn't be there in person, but I'm going to tell you a little bit about our work trying to understand sound localization. So many sound sources in the world are spatially localized, right? So they come from a place. And localizing sound sources is a critical ability for both humans and machines. So for instance, if objects are out of sight, they're behind you or behind an occluder, or if it's dark, or if you need to find a sound that's creating sound somewhere in the world. In all these cases, you need to localize where that sound source is coming from using audio. And the problem is interesting because the source location is not explicit in the audio signal. So it's also not explicit in the ear. So the cochlea, which is the organ in the ear that does the sensory transduction, contains a map of frequency, not space, okay? So how do we do it? Well, the basic outlines of the problem have been, at least people have felt like they've understood them for decades. And so the classical story that's in all the textbooks is that there's three main types of cues to a sound's location. So two of them arise from the fact that you have two ears. So this is a setting in which there's a sound source that's off to the person's right. And so the sound propagates through the air, and it will arrive at the right ear a fraction of a millisecond before it arrives at the left ear. Okay, so there's this tiny time difference, but it's reliable and it can be detected. In addition, because the head casts an acoustic shadow, at least for some frequencies, the sound that arrives at the right ear will be a little higher in intensity than the sound that arrives at the left ear. Okay, so we have these time differences, or ITDs, intraoral time differences, and level differences, or ILDs, that result from having two ears. Now, in addition, because of the fact that your outer ear, it has this kind of funny shape with lots of folds, the sound gets filtered on its way to your eardrum differently depending on where it comes from. Okay, so if it comes from above, it will arrive with a spectral coloration. It's a little bit different than if it arrives from below. And we believe that people they understand these cues, they've internalized them, and that's how you localize things in elevation. All right, so that basic story has been understood for decades. But real world environments have noise, they have reflections. Reflections in particular are a real challenge for localizing sounds because they tend to come from the wrong direction. And so localization in the real world is a hard problem. And so we've never actually had models that can actually localize sounds in real world conditions. And funnily enough, we actually don't know that much about how people localize sounds in real world conditions. And this is because in hearing research, there's been a very long tradition of doing very tightly controlled experiments. Okay, so typically in very controlled listening conditions with very controlled synthetic sounds. And so if you want to know how accurately does somebody localize an everyday sound in an everyday environment, it's very hard to find that information in the literature. So in our lab, we started out by actually trying to measure that. And so we built this thing shown here. So this was constructed by these three guys, Andrew Francel, Preston Hesson, and Johnny Stewart. And it's a big array of speakers. So we can present a sound from any one of these speakers and then ask a person who's sitting in this chair here to localize the speakers. They've all got kind of labels that you can't see here underneath the speaker. But the other thing that you'll notice here is that this is just a regular room. So this is a slightly scandalous setting in which to do a traditional hearing experiment. So we've got like HVAC and there's plenty of ambient background noise. The surfaces all reflect sound, stuff like that, right? So it's not the kind of setting in which people normally study hearing, but it's the one that we're interested in because it's a typical kind of real world room. And so we presented people with natural sounds from these speakers and then asked humans how well they could localize them. And so it turns out that even though we're dealing with this kind of fairly messy real world setting, humans are pretty good. So this is a graph that plots the mean absolute localization error in degrees on the y-axis as a function of the position of the sound in azimuth. So azimuth is the word that people use to refer to the horizontal angular position of the sound, okay, versus elevation. And so 0 means that the thing is right in front of you, minus 90 and plus 90 is off to the sides. And you can see that when sounds are in front of you, people are actually pretty accurate. They get less accurate as things move off to the side, but accuracy is still well below 10 degrees, okay? So people are all overall pretty good. The same is also true if you measure localization in the vertical dimension or elevation. So this is error in elevation as a function of the position in elevation. And again, people are under 10 degrees. All right, so even in these realistic conditions, humans are pretty good. And the question is like, how do we do that? So our research group at MIT is called the Lab for Computational Audition. We work at the intersection of psychology and neuroscience and engineering. And our main long-term goal is to build good predictive models of human hearing. So what we'd like to end up with is a computer program that can take sounds as inputs and that can make all the kinds of judgments that a person can make about sounds, even in realistic conditions. And we think that if we're successful in achieving that goal, it will transform our ability to do a lot of interesting things, in particular to make people hear better. Okay, so I'm not explicitly in the business of machine perception, but our goals kind of overlap a fair bit with people in machine perception in the sense that we're trying to build working systems that actually kind of can do things with real world signals. And so there's a lot of interesting points of contact, as you'll hopefully see during the talk. Okay, so how should we do this, right? So we got this situation where we know a fair bit about the ear. We have pretty good models of what actually happens in the ear, right? And then there's this big white box here, which is the rest of the auditory system. And like the traditional way to go about this research program would be to do experiments to learn various details of the way the auditory system and the brain works, and then try to build those into a working model. And I have become deeply pessimistic about the prospects of that as a research program, mainly just because it's pretty clear that what's going on inside this box is very complicated. And I think we would have to sit around doing experiments for a really long time in order to get enough information to pin down the things that are going on there with enough detail to build a model with the precision that we need, okay? So I've been really drawn to the fact that there's a few other things that we can leverage. And one is the fact that the sounds that come into our auditory systems that we have to hear on a daily basis are generated in the world by lawful physical processes. And so they're very, very non-random, right? They're a very tiny subset of the space of all possible sounds. Okay. And in addition, we know something about what the auditory system what kind of behaviors we can carry out, right? So we can recognize sounds and localize them, things like that. And so the hypothesis that we're working with is that the auditory system is fairly well optimized for natural behavior, and that as a consequence, it might be pretty highly constrained simply by the demands of real world sounds and environments and tasks, and maybe also the fact that you're hearing through a cochlea, okay? So the question is whether we can just use machine learning to learn a solution to the same kind of problem that a person is solving, and whether that's gonna actually give us a pretty good model of what people do. So the approach that we typically take is to hardwire a model of the cochlea to be faithful to what we know from biology, and then to kind of learn all the other subsequent stages of this auditory model with a neural network. And I should emphasize that in general, we don't make any attempt to place biological constraints on the model, other than the fact that it's kind of getting input from a simulated cochlea, and that it's doing a task that is biologically important usually. And we employ some kind of common sense principles when we design these things, but really I wouldn't call them biological constraints. And so as a consequence, it's really not obvious whether like the systems that you would build in this way would reproduce human behavior to any extent. So when we build these models, we use all the standard neural network tricks that everybody in this room is no doubt familiar with. The models are typically convolutional in time and frequency. And we train them up in the usual ways. And so the big question in the case of building a model of sound localization is where to get labeled data. All right, so we initially started off trying to do supervised learning, and the question is where do the labels come from? And it's pretty difficult to get real world data where you know the sound source locations, at least at scale. And so Andrew Francel, who's a very talented PhD student who just graduated a couple months ago, he's now at Meta, he decided to try to train a model using a virtual world. So we've now got pretty good acoustic simulations of the world. And so we can take a recording of a natural sound and some noise sources and then render the audio that would enter the ears of a person if, say, they were at this location here, listening to a sound source at the location in red with noise sources at the black locations. Okay? And that will produce stereo audio signals. And I mentioned earlier that there are these important acoustic effects that kind of happen as a consequence of the head and torso and outer ear, whereby sound that is reaching you undergoes a complicated series of reflections, and as a consequence gets filtered differently depending on where it comes from, okay? And so we incorporate those effects into this room acoustic simulator using head-related transfer functions that are recorded from a mannequin that's a standard model of the human head, okay? All right, so all of this ends up giving us stereo audio. We pass that through models of the cochlea, and that's the input to a neural network that has to estimate the location of the sound in azimuth and elevation, which of course are the generative parameters that we're providing to the simulator. Okay, so you can do this, and Andrew got this thing to work, but the question always when you're doing things in virtual worlds, as everybody knows, is like, are they actually going to transfer and do something useful in more realistic settings, okay? So the way that Andrew assessed this is by making recordings from an actual mannequin sitting in an actual room in our lab. So this is a very special mannequin that's got microphones inside its ears. And so you can make recordings of binaural audio with sounds placed in different positions around the mannequin, okay? So again, real world room with like HVAC noise and reflections and all the kind of complicated, messy stuff that happens in an actual room. And we were pleased to see that even though this model is just trained in this virtual world, it generalizes reasonably well to this real world setting. So this is a graph that plots the actual position of sounds on the x-axis and the judged position here. And you can see that things land pretty well on the diagonal, okay? So we've got a model that can actually localize things in the real world, which we were excited about. Now, people have been studying human sound localization for a really long time, right? So there's a huge and rich experimental literature. And this row of graphs shows an example of a set of experiments that people have run over the years. And each one of these graphs measures something different about how people localize sounds. And if you were a sound localization researcher, you would know and love each one of these graphs. The details of them don't matter though for our main purpose today, okay? And so we can kind of think of these graphs as sort of describing the strategy that humans use when they localize sounds. All right, and so the question that we asked is, will this system that we built that solves this problem of sound localization using the same kind of input and settings that humans operate in, would it end up reproducing the same kind of strategy that we see in humans, all right? So again, I should emphasize there's no other biological constraint that's placed on the system, and so you might expect that it would learn some completely different strategy. And so the way that this works is you just render each experimental stimulus that's used in each of these experiments, you present it to the model, it makes a localization judgment, and then you can run the same kind of data analysis procedure and get the same kind of results graph. And when you do that, and what you can hopefully see by kind of comparing the top row and the bottom row, you find that the model qualitatively and often quantitatively reproduces all these classic effects from the human spatial hearing literature, okay? And these show all kinds of different things. I'll just give you one example that's kind of interesting. So this is a classic experiment that was done in order to test the role of the filtering of the outer ear in our ability to localize sounds. Okay, so this is a picture of somebody's outer ear. This is a graph that shows the results of an experiment where you have people localize sounds in the lab. So they were presented with a grid of locations. That's the dashed lines here. And then the solid lines connect the average localization judgments of human listeners. And the fact that the solid lines overlap the dashed lines means that humans under normal conditions are pretty good, both in azimuth and in elevation, okay? Now, in this experiment, so this is a classic from John Van Opstel's lab, they then put these plastic molds in people's ears. And that has a consequence of changing the transfer function, right? So the ears are still kind of filtering sounds in a direction-specific way, but they do it differently than the person is used to. And when you put those molds in their ears, something really interesting happens, which is that people lose the ability to localize an elevation. So you retain the ability to localize in the azimuthal dimension, but you lose the ability to localize an elevation. And this is pretty compelling evidence that people are actually using the spectral filtering of their outer ear to localize in the elevation dimension. And so we could ask whether the model is using similar kinds of cues by doing the same kind of experiment on the model. So it was trained with a particular set of head-related transfer functions, and we can swap in a different set of functions, okay? And you see a very analogous effect. So on the top graph, you can see that the model is localizing accurately when it's tested with the transfer functions it's trained on, and then you give it a different set of transfer functions from a different human, and it retains the ability to localize in azimuth, but loses the ability to localize at elevation. All right, so that's just an example. Okay, so we've got this system. It's been optimized for the sound localization problem, and it's kind of recreating the behavioral phenotype of human spatial hearing to a pretty good degree. And so you might say, okay, well, that's kind of cool, you know, but what's the scientific contribution? Like, what do we learn from this? And I think what we learned from this is that like all these perceptual traits seem to be a consequence of simply a consequence of having been optimized for the task. Okay, and in some of these cases, you know, people already had pretty good intuitions that was the case, but for many perceptual traits, that we just never had that kind of understanding. And my favorite example of this is the one that's shown here. So this is an experiment that measures how well people can localize multiple sounds at the same time. Okay, so this was done by Zhang and Yost a few years ago. The human participant is kind of seated in the middle of this circular array of speakers, and some number of the speakers play sounds at the same time, okay, between 1 and 8. And the person just has to indicate which speakers are playing a sound, right? And the graph here plots the reported number of source locations versus the actual number of source locations. And so you can see that for 1, 2, and 3 sound sources, people do pretty good, but then after that, they dramatically undershoot. So it seems that human sound localization is limited to about 3 or 4 things at one time. Okay, so this is just a result. It came out a few years ago, okay? And just given this, like, it's really not clear where this limit comes from. Like, you might imagine that maybe in order to localize things, you have to pay attention to them. We often think that we can only attend to a few things at once, so that might be part of it. But it could also just be that, like, when you get lots of sound sources that are on at the same time, the cues start to interfere with each other, and really there's just not enough information there to pull out the locations. Okay, and so the model can give us some insight into this, because when we run the model on the same experiment, you get a very, very similar results graph. Okay, and what I should emphasize here, and this is true for the previous graphs as well, is that the model is not being fit to match human data in any way, right? We just optimize it for the problem, the model gets frozen, and then you run it in the experiment. Okay, and the fact that it is exhibiting a similar limit suggests that this property of human sound localization really reflects an intrinsic limit on like the information that's available when you're trying to solve this problem. Okay, so it can show us that these otherwise mysterious aspects of perception really result from optimization for the problem. So now, do these traits kind of reflect a strategy that is adapted specifically to like the kind of world in which we live in? And we were able to ask this question pretty straightforwardly because of the fact that the system is trained in a virtual environment. So we can take the virtual environment and then kind of alter it in ways that would be impossible to do in the real world. And we did 3 versions of this. So in one case, we made the environment anechoic. All right, so this is a situation where every surface absorbs all of the sound that impinges on it. So there's no reflections. So this really never happens in kind of natural conditions. You can construct anechoic rooms if you work really hard to build an atypical environment, but normal rooms, the surfaces always reflect sound. Okay. We could also create a noiseless environment by getting rid of all background noise, or we can make the sounds that system had to localize unnatural, in this case by making them bandpass noise. Okay, so these are three different ways to kind of change the world in which the system is optimized to deviate from what we think are natural conditions. So we then trained the system in all of these three different conditions, ran it on all of those experiments that I showed you, and then asked the extent to which the experimental results would resemble those of humans. And so we, for every experimental result, we compared the model to humans, we came up with a measure of dissimilarity, and we just aggregated that across everything. So this is just an aggregate measure of human model dissimilarity. So the higher up the bars are here, it means the more different the model is from humans. So if you test the model that's optimized in normal or natural conditions, this is what you get. And we don't expect this to be zero because the human data is not perfectly reliable. So you're just going to get some number, okay? But the important thing is that in each of these three alternative training conditions, each of which we think of as less like the natural world, the model behaves less like humans overall. So this is evidence that the sound localization strategies that we see in humans are, in some sense, a consequence of being optimized specifically for the natural world. And in some cases, these deviations actually end up being pretty interpretable. And one of the clearest cases is something called the precedence effect. So the precedence effect is a classic effect in hearing, and it refers to the fact that when people localize sounds, their localization judgments tend to be dominated by onsets, like the very first part of a sound. Okay, so the setup in which this is measured is shown in this schematic here in the upper right. So you have a person, they're typically seated in an anechoic chamber, and there'll be two speakers that can play sounds, one to the right and one to the left. And the speakers emit clicks, and they do so with a slight time delay. Okay, so this one is the leading speaker, and this is the lagging speaker. Okay, so these time delays are pretty short, but they're still significantly longer than the interoral time delays that normally happen. So the stimulus that enters the two ears is shown here in the upper left. Okay, so you first hear the leading click, and that's coming from the right, and so it arrives at the right ear shown in red, a little bit before the left ear shown in blue, and then after some delay, the lagging click arrives, and because that's coming from the left, it arrives at the left ear a little bit before the right ear. So this difference between the blue and the red is the interoral time difference, and then this longer delay is the delay between the two clicks. Now the precedence effect, it refers to the fact that when you hear the stimulus, if the delay is short, like a few milliseconds, people report hearing one thing, and they report hearing it coming from the leading location, all right? So they say that the stimulus is coming from 45 degrees to the right, even though there's actually two clicks, one from the left and one from the right. And this has often been proposed to be something that would help you deal with echoes, and I'll get to that in a second. All right, so you see this in humans, and the model exhibits a very similar effect. So you give it the stimulus, and when there's a delay between the clicks of a few milliseconds, the model says that there's one thing kind of coming from the right, and then as the delay gets too long, the effect kind of dissipates. And so like I said, the working hypothesis that people have had for a long time is that this is an adaptation for reflections. So this is a picture of a person in a room listening to a sound from a speaker. And you can see that the sound reaches the person through all these different paths, right? There's the direct sound though, which is shown in green. And the direct sound is the one kind of direction in which the source direction is accurate, right? It's the one that is actually there in the world, right? The sound is reaching you from where it's coming from. In all the other cases, the sound arrives at your ears from some other kind of direction. But the other thing that's kind of special about the direct path is that it's the shortest. And so the direct sound is what hits you first. Okay, and so the idea behind the dominance of onsets and localization is that it would help you in an environment that's where there are reflections, because the very first little bit of the sound is the one that presumably has the most accurate direction information. All right, so that's kind of this, it's one of these just so stories that people often kind of give in perception. And it's never really been testable, of course. We can test this in our model by asking under which conditions an optimized system will exhibit this effect. Okay, so we have these three different unnatural alternative environments. And one of them in particular is very special with respect to this hypothesis because it's anechoic, there's no reflection. Okay? So for the other two environments, we still see this same kind of qualitative effect. But what's quite interesting is that for the system that's optimized in the anechoic environment, the effect completely goes away. All right, so this is helps substantiate this idea that this particular classic perceptual effect is actually an adaptation for dealing with reflections when you have to localize things. All right, so the overall picture that's kind of emerging from this work is that the behavioral traits of audition, here I'm talking specifically about sound localization, are strongly constrained by real world sounds and the environment, such that we can actually get a pretty good model of sound localization just by optimizing a system for the problem. All right, so you might ask, well, it's nice that we can kind of reproduce all these known effects, but can we predict anything new? So we did this experiment that I mentioned earlier where we measured localization of natural sounds from the speaker array. And we used a pretty big set of diverse natural sounds. So things like crumpling paper, crying, scissors cutting, dial tones, et cetera, et cetera. All right, so just pretty much everything we could get our hands on. Okay? And so previously I showed you aggregate results where if you average across all sounds, you can show that people are on average pretty accurate. But you can also look at how accurately individual sounds are localized. Okay, and it turns out that some sounds are more accurately localized than others. So this is like a subset of the sounds that we presented, and these graphs are plotting the mean absolute error. On the bottom, it's in elevation, and on the top, it's in azimuth. Okay, and each x-axis position is a different sound. And so you can see that there's a fair amount of variation from sound to sound. So a lot of them are localized pretty accurately, but there's some that are significantly worse. The ones that are harder to localize in elevation also tend to be harder to localize in azimuth, but not always. So there's a lot of kind of interesting variance in what happens with human localization. And so we wondered whether we would be able to predict this with our model. And so this graph compares the mean absolute localization error of the model on the x-axis for that of humans on the y-axis. So each dot is a different sound, okay? And you can see that there's a pretty good correlation here. So sounds that are less well localized by humans tend to be less well localized by the model. Now you can also see that the model is overall less accurate. And we think it's probably overfit to the set of training sources that we used. So when we started on this project 5 years ago, it was not that easy to get lots of recordings of isolated single sources. So we didn't have that many on our training set. So we're currently trying to build a larger training set given kind of the resources that we have today to improve the accuracy of the model and potentially the match to human data. But it's nonetheless kind of encouraging that we can predict human localization accuracy to some extent with this machine system. And the long-term goal would be to potentially use this, for instance, to design auditory displays where you could use a model to figure out what kind of sounds and where they should be positioned in order to create a display where people will hear the right stuff in the right places. Okay. I just want to end very quickly by considering this question of how humans acquire their sound localization abilities, right? So I've shown you that we can build a pretty good model of human sound localization by training it to localize sounds with supervision. And the question is that like a realistic account of how people acquire their abilities? And so, one way to think about supervised learning is that it's kind of a stand-in for evolution, right? That each training example maybe represents an instance of natural selection. So it's possible that we're just born with sound localization abilities. But that doesn't seem to be the case. So there's been a fair bit of work measuring sound localization in babies. And this is a graph that shows the minimum audible angle for a human as a function of their age in months. And so you can see that babies start out not being particularly good and then get better and better over time. Okay, so it improves quite a bit over the first 2 years of life, probably beyond, and that suggests that the ability is probably not innate. All right, so the question is, could it result from supervised learning during development? And of course, then the question is, well, where do the labels come from, right? And so vision is a priori plausible as a learning aid, and everybody in this room knows that there's lots of interest within computer vision about leveraging the fact that you've got both vision and hearing and using one modality to learn about the other and so forth. Okay, so it's a really nice idea. And you might think that something like that is actually happening in humans, but as far as I can tell, there's actually no evidence that humans rely on vision to learn sound localization. And really the key kind of relevant piece of evidence comes from individuals who are congenitally blind. So you would think that if you critically rely on vision in order to learn to localize sounds, that people who are congenitally blind would be substantially worse. But if anything, localization is somewhat better in the congenitally blind. All right, so we don't think that people are relying on vision to learn to localize sounds. So we got interested in an alternative possibility that you might be able to leverage self-motion. And so the idea here is that scenes in the world tend to be stable on short time scales. So if there's an object that is emitting sound at one moment, it's probably in the same location at the next moment. And humans have access to their self-motion from vestibular and proprioceptive signals. And so we thought this could be a free training signal, right? The fact that if you assume that sounds in the world tend to be fixed and you know how to move, you might be able to learn the relationship between the signals in your ears and the locations in the world. Okay, so the idea is really simple. We just tried to implement a version of this using contrastive learning. We want to compare situations where there's no or a very small head movement, and then try to maximize agreement between the latent representations of the sound signal versus situations where there's a large head movement where we want to minimize the agreement. So we use the same virtual acoustic world to generate auditory scenes. These are 1-second snapshots at different head positions. The model is trained using momentum contrastive learning. And then we evaluated, after it's learned, we evaluated the learned representation with a location decoder that's trained on the embedding representation. And I'll just show you how well this works. This is a summary graph showing the model localization error after training. So we got error on the y-axis measured at different source elevations. And you can see that the model does okay. It does certainly way better than chance, okay? So on the order of like 10 degrees of error, so it's not so bad. It's nonetheless significantly worse than what we found with supervision, and significantly worse than what humans would do in this situation. So we think this is sort of an intriguing idea for how humans might learn to localize sounds, but it certainly needs more work in order to sort of get this working. So at this point, it's just a promising idea. Okay, so just to summarize, I've told you a little bit about our work building new models and making new measurements of human sound localization. We find that models that are trained to localize sounds in a virtual world reproduce a pretty large set of human behavioral traits, including many classical psychophysical results. The model can give us insights into the origins of behavioral traits. So a lot of traits seem primarily to be a consequence of natural past demands. We can often link them to properties of the world. And the models give us some ability to predict localization of particular sounds in real world conditions. And we think there's a potential maybe to explain localization using self-supervision from head movements, but that's kind of very much work in progress. So the work that I told you about today is the PhD thesis of Andrew Fransel. He just got his PhD. He's now at Meta with help from Preston Hess and Ajani Stewart. And I will thank you for your attention. And if there's time, I'm happy to take questions.
Looks like there's a lot of them. If you're online and attending, you can just send them into the chat.
Hey Josh, great talk. I have a question. So when you said that people not having visual impairment, they're better at localizing sounds. So why do you think that happens?
Yeah, I mean, it's probably just because when you're blind, you're more reliant on your auditory system. That's my guess. Yeah, so they just sort of, they probably have more practice at some level. Yeah, but it certainly doesn't, you would think they'd be worse and they're better, and it's probably because of practice. It just doesn't provide any evidence that you rely on vision, which I think is really interesting, right? Because it's like super plausible that you would actually leverage the different modalities to learn. And I don't want to claim that there's no situation in which you use vision to help you hear or to learn to hear. It's just in the localization setting, we don't have any evidence.
Okay, like one other question. So when you said that you use a cochlear model, so what kind of model is that? Does it just decide the kind of spectrograms you use, or is it like adaptive or something?
Yeah, so we used the most realistic models that we can, depending on the setting. I mean, it's usually just constrained by practical considerations. But in this particular project, the model is a linear filter bank that's modeled after the cochlea. The responses of that are half-wave rectified and then downsampled to 8 kilohertz to kind of reflect the temporal limitations of the ear.
Okay, thank you.
All right, who else has questions?
Thanks for the great talk. You talked a lot about localization, and you were talking about elevation and azimuth, and was saying that elevation is something that is much more sensitive towards your personal ear shape. You did not really talk about depth or distance, which would be the missing component to get exact 3D localization. Can you comment on that? Is that also very personalized, or is that a general problem because, I don't know, it's a more fuzzy signal than elevation and azimuth?
Yeah, that's a great question. Yeah, so we did not model that, and mainly due to practical constraints. I mean, that's something I'd really like to do. But yeah, distance. So in general, I think distance perception, when things are very close to you, that will rely on kind of learning your specific transfer functions. And when I say close to you, I mean kind of within like about a meter. If it's further than a meter away, we think that you mostly rely on reverberation cues that are probably not going to be person specific. People certainly have some ability to do it, but yeah, once it gets further away, it becomes pretty fuzzy, as you say.
Thanks.
Hi. You have shown that we can hear or we can localize certain sounds better than others. So is there any logic in behind about which kind of sounds we can localize better, or it's about frequencies, it's about familiar sounds, naturalness?
Yeah, great question. So it's certainly like the sparsity of the spectrum does have something to do with it. So the sounds that tend to be more poorly localized, they just don't have as many frequencies in them usually. But it's not just that. So like if you take simple measures of spectral sparsity, they don't predict all of the variance that the model predicts. So there's sort of other properties that, they're learned by the model and we don't yet completely know what they are. I don't know the extent to which we should expect to end up with like a perfect, very simple, verbally like articulatable explanation of that. It may just be that in the end we have a system that is optimized for the problem that could kind of predict what's easy to localize and what's not, and that's basically going to be the description that we use.
Okay, thank you.
Hi. So in humans, the number of ears is limited to 2, right? But for computer models, you can have many more ears. So do you think the model can achieve like superhuman localization abilities when you have many more ears, or are you interested in that kind of research?
Yeah, I'm sure you can do better with more microphones, and I'd love to have somebody else do it. I'm in the business of building models of what people do, and so we stick to like a cochlea and with 2 ears, and yeah, you could certainly do better if you had a big microphone array. That's sort of a separate project though.
Thank you.
Any other questions for Josh? Well, if not, let's thank the speaker again. Thanks, Josh.
Thank you.